This video looks at how to incorporate constraints into a GPC law. So the first two videos in this chapter have demonstrated through simulation examples and illustrations and so on that constraint information must be included systematically into a control design. The optimum constrained performance can be far away from the unconstrained optimal, and moreover it can also be far away from saturation control. What we need to do then is ask ourselves, if we need to include constraints, how do we do it? So this video is going to show how simple constraints on inputs and outputs can be incorporated into GPC. First then, remind ourselves of the structure of the problem. We've got a quadratic programming problem that looks something like this. We've got a quadratic performance index and we have linear inequalities. Now chapter 2 has already shown how GPC can be expressed as the minimization of a two-norm cost. So if you look in chapter 2, you'll see we have the quadratic bit here, delta U future transposed times S times delta U future, and then we've got a linear bit here, delta U future transposed times something over here, which I've called, you'll notice, A, and over here I've got this definition S. So we already know that GPC has a quadratic performance index that we can formulate like that. So the real question is, how do we formulate these linear inequalities to go with it? Let's look at typical constraints then. We might have upper and lower limits on an input. So there you can see a lower limit, input UK, upper limit, and that has to apply for all samples. We can also have upper and lower limits on the rates. So the input can only change so fast. And again, you'll see there's the rate delta UK. And we can also have upper or lower limits on a state or an output. So here I've demonstrated it on outputs, but it could equally be on the states. And finally, it's also possible to have mixed constraints, and what we mean by that is constraints which actually combine, say, state 1 with state 2 and so on. But I'm not going to go into that in detail. I'm going to let the viewers work that out by themselves should they need it. How then do we express input rate constraints using a matrix inequality, which is what we want? Well, the first step, this is important, is just to write out every constraint as a separate inequality, and you'll see that's what I've done here. I've said delta UK has to be less than the upper limit, delta UK plus 1 has to be less than the upper limit, delta UK plus NU minus 1 less than the upper limit, and similarly if I look at the lower limit, for example, minus delta UK plus 1 has got to be less than or equal to minus the lower limit, and so on. We also need to remember that within GPC the input is fixed after the first NU samples, and therefore we also know this, that delta UK plus NU plus I becomes 0 for I greater than or equal to 0, which is why we only need to deal with these particular constraints here. Next, what I want to do is put those inequalities into a single matrix vector expression just to make my life easier. And that's relatively straightforward to do. So here's the expression here, and you'll notice this top row, which is 1, 0, 0, 0, multiplying onto delta U future here, essentially gives me 1 times delta UK is less than or equal to delta U over bar, which is this expression here. If we look at the second one, delta UK plus 1 less than or equal to delta U over bar, you'll see it's this 1 multiplied by this value here and this value here. And hopefully the rest of that construction is self-evident. So if you need to pause the video here just to look at this construction a little longer, then please do that. But the bottom line is we're defining this matrix, C subscript delta U times delta U future is less than this vector over here. So our inequalities can be summarized using this compact form here. What about input constraints? Well, again, the key is to write out every input constraint separately. So I've got the input is less than an upper limit at sample k, the input is less than an upper limit at sample k plus 1, and so on, and similarly minus the input is less than minus the lower limit at sample k, and so on down. And again, remember that after NU steps the input becomes constant, so I do not need to test the inputs further into the future because they're implicitly checked by the nth input. Again, what I want to do next is put these into a single matrix vector expression, and hopefully you'll see this is exactly the same as rate constraints. I've now got CU times U future is less than or equal to this vector, which has got the upper limits and the lower limits. And again, I won't dwell on that because this is identical to 2 slides ago. If you need to pause the video and look at this slowly, then please do that. So in summary, we have a matrix C subscript U times U future is less than or equal to D subscript U. Now, you'll notice in GPC that we have a simple relationship between the inputs and the rates. So here, for example, the input at sample k plus I is the input at sample k minus 1, and that's important you notice it's k minus 1, plus the change at sample k, the change at k plus 1, all the way up to the change at k plus I. And the reason we've done that is you remember that these delta u's are our degrees of freedom. Now what this means is I can express my future inputs in terms of my future increments. So UK is going to be 1 times delta UK plus UK minus 1. UK plus 2 is going to be delta UK plus delta UK plus 1 plus UK minus 1, and so on. And so I'm going to end up with this simple expression here, that the future values of U are given by this matrix E times the future values of the increments plus this L matrix times UK minus 1. And you'll see E is defined here and L is defined here. So again, do pause the video if you need to look at this a bit more slowly, because this expression is quite important. So now what I'm going to do is look at my input rate constraints, my input constraints, and my relationship between my future inputs and future rates. So there's my compact form for the rate constraints, my compact form for the input constraints, and my relationship between U future and delta U future. If I combine these 3 equations together, then I get this. And hopefully it's obvious that this top one is simply gone to the top row here. I've just mapped it straight across. And the input constraints are just the second block down here, but the difference is where I've got U future, I have substituted this expression in here. So you'll see I've got CU times capital E times delta U future, CU capital L times UK minus 1. And so now what have I got? I've got a nice compact expression which is in terms of my degrees of freedom and things which are known. So there's my linear inequalities that I need to satisfy to ensure that my predictions satisfy input constraints and input rate constraints. What happens if we add output or state constraints, which we said could be written something like this? Well, again, it should be obvious, using the same notation as earlier, that I can very quickly come up with an expression of this form here. Cy times y future is less than or equal to dy. Well, dy has got all these upper limits and all negatives of the lower limits and so on. So that's exactly the same in terms of structure as earlier. Next, what I do is I say I happen to know my output predictions are given by this expression here. Now that was covered obviously in the earlier chapters, so I can substitute that directly into this expression here. So what I'm going to do is I'm going to take this bit here and I'm just going to substitute it in directly here and see what I get. And so this is what you get. You see you get Cy times H delta U future, Cy times P delta U past, Cyq y past is less than or equal to dy. So again, a nice compact expression, and the key thing is my degrees of freedom are in there. So finally, let's combine all 3 sets of inequalities together. So I've got my rate constraints, my input constraints, my output constraints, and you'll notice I've expressed them all in terms of my degrees of freedom to make life simple, and these are the inequalities you end up with. Here's my dependence on the degrees of freedom. You'll see rate constraints the top block, input constraints the next block, output constraints the bottom block. I've got some variables which I know. UK minus 1 is known, delta U past is known, Y past is known, and then I've got the D's, which are the actual limits on the rates, the inputs and the outputs. Now it's convenient to separate this into parts which are known and parts which are not known. So obviously this bit on the left is my degrees of freedom, whereas everything on the right is known. And so I can now give a compact expression C delta U future less than or equal to D, where you'll notice D is all of these bits over here. Now here's a key observation. C is constant, this capital C matrix, but the D vector is time varying. It changes every sample because it depends upon the past input changes, and the past output. So my linear inequalities change every sample. So there's a summary. The input and output constraints can be concatenated into a single matrix vector inequality of this particular form, and in particular this D depends on all the limits and it depends on past data and so on. So it depends on the limits on the input rate and the output, which are fixed. It depends on past measurements, past inputs and outputs, which vary with time, and also, and we'll cover this later, it may also depend on the set point disturbances and so on. And hence the key thing is this D is actually a function of the sample instant and must be updated every sample. If you wanted to extend this to the multivariable case, because I've just done the single input, single output case here to keep things simple, then actually there's nothing different to do. You simply write the inequalities in terms of vectors rather than scalars. But if you look at the structure of all the matrices and all the inequalities that we've written, nothing changes. You can use an identical structure. The only difference is where you put ones or zeros before. Now you will need to put an identity matrix of suitable dimension or a matrix of zeros as appropriate. But otherwise, the structure and the algebra will mean it will be exactly the same. Let's do some demonstrations then on MATLAB, and the code for this is in the GPC folder if you want to find it. And in essence, we're going to show how you can construct these constraint inequalities for a system. The main file is mpc_constraints.m, which does inputs and input rates only, and it will generate for you the C matrix, the DD matrix, which is the fixed bit, and the DU matrix, which depends on the past value of U. If you want to include output constraints as well, then you go to this file mpc_constraints2, and that will also generate for you this DDU vector, which multiplies DU past, and this DY vector, which multiplies Y past. Now you'll notice that I've used CC here rather than C, and the reason I've done that is in MATLAB is to avoid confusion with the C matrix, which you might be using for state space models. Here's the first example then that we're going to look at. So video_53 example 1. There's a CISO case and there's a multivariable case. And the key thing we want to look at is how do we generate this matrix here, CC, this vector here, DD, and this vector here, DU. You'll notice this example has got no output constraints. So let's just go and have a look. There it is, video53 example 1. So the CISO example is here. So I can, for example, run that with F9, and if I now go and look and see what we've got here, you'll see here's my CC, and you'll notice it's got the structure that we expected from the vectors, this identity for the rate constraints, minus identity, and then this lower triangular ones for the upper input constraint, and this lower triangle of minus ones for the lower input constraint. If I look at DD, which had just the constraints, you'll see it's got the delta U max in the top blocks, the U max here, and the U min down here. And the final one was it DU, I think. And there you can see we had zeros at the top, had no impact on the rates, minus 1 for the upper input, plus 1 for the lower input. And if you compare that with what we've done in the slides, you'll see it's what we expected. If you want to run a MIMO example, here it is. So run that one, and here you'll notice, of course, things are much bigger. Now, the bottom one is this DDU, and you'll notice DDU has now got 2 columns because there are 2 inputs. So 1 column for each input, because DU multiplies the previous value of the input. And therefore you see this minus identity, plus identity, plus identity. So where you had 1s in the CISO case, you have identities in this case. If you look at CC, which would be quite large, and here I've just taken NU equals 2 to keep things visible, you see upper rate constraints, we've got 2 identities there. Lower rate constraints, 2 minus identities, and then if you look carefully at this matrix here, you'll see it's a sort of a block lower triangle of identities. So you've got an identity there, and an identity here, and so on. So the structure follows, but what you can do is look at these files in your own time and check that it makes sense. Okay. Now, next one, we've got video 5.3 example 2, video 5.3 example 3, which include output constraints. So now what we're looking for is we're expecting to get this CC, this DD, a DU, a DDU, and a DY. So those are the variables that we want the file to produce for us. So let's just have a look. We'll go back. There it is. If I look at example 2, so here it is. Now I'm just going to run it straight away. Press F5, and then let's have a look. And it gives you whose, so it tells you how big are the things that it's produced. So CC, 22 rows, 3 columns, because I've chosen NU equals 3. DD, 22 by 1, because that's just got the constraints in it. DDU, 22 by 1, because there's just 1 input. DU, 22 by 1, because there's just 1 input. Oh, sorry, 1 passed input. But you'll notice DY is 22 by 2, and the reason for that is if you look at Q, the prediction matrix, you notice that Q had 2 columns, and therefore DY has 2 columns. Now if you go to video 5.3, example 3, this is a multivariable example. So if you look at the top, you'll see it's got the A's and B's. It's got 3 outputs and 3 inputs. I've chosen an output horizon of 4, an input horizon of 2. They are quite small, but this is just for illustration. And so how big are these matrices going to be? And here you can see the answer. Even with an output horizon of just 4, my CC has got 48 rows. An input horizon was just 2, and I've got 6 columns. So you notice that these are now becoming quite large. The dy is 48 by 12. Okay, that's just multiplying y past. But you're beginning to see, even with low horizons, I'm getting very big matrices here. If I was to go here and change ny to something more realistic, let's say 15, change nu to something more realistic, let's say 4, and run that. How big are my inequalities now? And you can see 138 by 12 is CC, 138 inequalities. So they're becoming very big very quickly. Okay, so if we finish, this video has shown how input and output constraints over specified horizons can be represented by simple matrix inequalities for GPC. And the MATLAB code is provided to build these matrices. So we need to build the CC matrix, this DD vector, this DU matrix, DDU matrix, and DY matrix. So those are what are used for GPC, and we've provided a piece of code to build them for you. It's noted, however, that the construction of these inequalities results in some large dimensional matrices, even for relatively small horizons and relatively low system dimensions. I only had a 3 by 3, which is quite small by predictive control standards, and you saw how rapidly the number of inequalities grows. And the final thing that you need to remember, and we must emphasize, is this D vector must be updated every sample, because it depends on past inputs and past outputs.